Welcome to the deep dive.
Glad to be here.
Today, we're digging into a really interesting research paper. It's called Beyond the 80-20 Rule. High-entropy minority tokens drive effective reinforcement learning for LLM reasoning.
Yeah, it's quite a title, but the core idea is fascinating. It looks at how large language models get better at reasoning.
Right, and we've got the paper right here. Our plan is to really unpack how these models improve through this technique, RLVR, it's reinforcement learning, with verifiable rewards.
And specifically, we'll be looking through the lens of something called token entropy, trying to see what patterns emerge in the model's thinking process.
So yeah, our mission is to pull out the main takeaways, understand what's really driving the improvements when these models learn to reason better.
Let's dive in.
Okay, first things first. This term, token entropy, what are we actually talking about here in the context of an LLM spitting out text?
Right, so imagine the model is generating text one token after another. A token could be a word, part of a word, punctuation. At each step, before it picks the next token, the model calculates probabilities for all possible tokens in its vocabulary.
Okay.
Token entropy is basically a measure of the uncertainty in that probability list. If the model is super confident about one specific next token, like say 99% probability,
Then the entropy is low. It's certain.
low entropy, yeah. But if the probabilities are more spread out, maybe several tokens look plausible, then the model is more uncertain.
And that means high entropy.
High entropy.
Yeah.
It reflects how much choice or maybe confusion the model has at that specific point.
Got it. And this paper looks at entropy within chain of thought reasoning, those step-by-step explanations models give. What kind of patterns did they find there?
Well, this is where it starts getting really interesting. They analyzed these COTI outputs and found something quite distinct.
Huh.
The vast majority of the tokens the model generates, they actually have low entropy.
Really? Most of them.
Yeah, most of them. Think about it, when you're writing or speaking, a lot of it is just following grammatical rules, finishing common phrases,
Like adding ing to a verb or putting a period at the end of a sentence.
that kind of thing. The model is often just following the path, completing standard sequences, filling in predictable bits of code or logic.
Hmm.
There's not much uncertainty there. These are the low entropy tokens.
Okay, that makes sense. But you said distinct patterns, so there's more to it.
There is, because amidst this sea of low entropy tokens, they identified a small but critical minority of tokens that have high entropy.
Ah, the uncertain ones.
Yes. And these aren't just random noise. The paper calls them forking tokens. They represent real decision points in the reasoning process.
Forks in the road, basically, where the model has to weigh different options.
That's a good way to put it. These are the moments when the model faces higher uncertainty, where it has to choose between genuinely different paths forward in its logic.
And what's special about these particular tokens? What role do they play?
Their function seems to be pivotal. They often act as bridges between logical steps, or they introduce a new concept, or signal a shift in the reasoning. The paper points to examples like words wait, or however, or thus, or suppose. Think how those words work. They mark a turn, a consequence, a hypothesis.
Yeah, they're not just filler. They guide the logic.
Right. Whereas the low entropy examples they show are more deterministic things like word endings, punctuation, predictable code snippets.
So low entropy builds the path, high entropy chooses the direction at key junctions. Did they test this idea?
They did. They ran experiments manipulating the entropy during generation. They used something called temperature scaling, basically a knob you can turn to make the model more or less likely to pick less probable tokens.
Yeah.
Higher temperature means higher entropy, more exploration.
Okay, so what happened when they tweaked the temperature?
They found that if they moderately increased the entropy, but only at those high entropy forking points, the model's reasoning performance actually improved.
Wait, making it more uncertain at those key spots made it better.
It seems counterintuitive, right? But think about it, if you're at a genuine decision point, maybe exploring a slightly wider range of possibilities, being a bit less certain initially, helps you find the best logical next step.
Okay, so allowing for more exploration right at the fork helps find the better path overall.
Seems like it. And conversely, when they forced the entropy down at those high entropy points, making the model more certain, prematurely reasoning performance got worse.
Wow, so that really highlights the importance of those specific moments of uncertainty.
It really does. It suggests these aren't just points of noise, but crucial junctures that benefit from a less rigid approach.
Okay, so we've got low entropy path following tokens and high entropy decision fork tokens. Now, how does the training process, this RLVR, interact with all this? RLVR is supposed to improve reasoning based on feedback, right?
Correct. The feedback often relates to whether the final answer of the reasoning chain was actually correct or valid.
So does RLVR change these entropy patterns? Does it make everything low entropy, for instance?
Interestingly, no, not fundamentally. The research found that during RLVR training, the basic structure of the entropy patterns tends to stay the same. The locations of the high-entropy forks don't seem to shift around dramatically.
So the model still gets uncertain in roughly the same places?
Generally, yes. It seems the underlying points of logical difficulty or choice remain similar.
But the model is getting better. So what is the training changing?
This is the key finding. While the locations are stable, the RLVR training primarily works by adjusting the level of entropy of those tokens that were already high entropy.
So it's fine-tuning the uncertainty at the forks.
That seems to be it. The paper shows figures indicating that the entropy of the vast majority of tokens, the low entropy ones, barely changes during training. It stays stable, but the entropy at those high entropy points, that's where the adjustments happen. RLVR is essentially learning how much uncertainty or exploration is optimal at those specific decision points.
So it's not a blanket change. It's targeted learning, right where the choices matter most.
That's what the data suggests. It's refining the model's behavior at the critical junctures.
Okay, this is fascinating. And it leads straight into the main experiment of the paper, right? They tested this idea directly.
They did. Given how important these high-entropy tokens seemed, they thought, well, what if we only apply the learning signal, the updates from RLVR, to these tokens?
Instead of updating based on every single token in the reasoning chain.
Right. Normally, the feedback signal, the policy gradients, would be used to tweak the model's parameters based on every token generated. Here, they restricted it.
How restricted?
In their main experiments, they only applied the updates based on the policy gradients associated with the top 20% highest entropy tokens.
So ignore the 80% low entropy path following tokens and just focus the learning on that top 20% where the model was most uncertain. What happened?
The results were pretty remarkable. Training with only this top 20% high entropy subset, it performed as well as, and sometimes significantly better than, training with all the tokens.
Better, just by focusing the learning.
Yeah, especially on larger models. They mentioned one case with Quen 332B, where focusing on the top 20% gave an 11-point boost on a reasoning benchmark compared to training on everything.
That's a substantial improvement from being more selective about the training signal.
It really is. And they also did the opposite experiment, which is just as revealing.
What was that?
They tried training only on the bottom 80%, the low entropy tokens.
The ones the model was already sure about.
Right. And the result? Performance completely tanked. The model didn't improve. It actually got worse at reasoning.
Wow. So focusing on the easy parts is actively harmful.
It seems that way. This is why they titled the paper Beyond the 80-20 Rule. It's not just that 20% of the tokens are important, it's that almost all the benefit from RLVR comes from optimizing that high entropy 20%.
And the other 80%.
They contribute very little to the actual improvement in reasoning ability, and focusing on them might even mess things up.
So the learning mechanism isn't about polishing every single step, but about getting better at navigating those crucial decision points.
That appears to be the core insight. It's about improving the choices made at the forks in the reasoning path.
Why does this targeted approach work so well, though? What's the mechanism they propose?
The thinking is that it significantly boosts exploration where it matters. By concentrating the updates on tokens where the model's probability distribution is flatter, higher entropy, the training encourages the model to really explore the consequences of different choices at those key moments.
So it learns more effectively about which branches lead to good outcomes.
That seems to be the idea. The paper suggests focusing on that top 20% strikes a good balance, enough exploration at the critical points without destabilizing the whole generation process.
And this benefit gets bigger with larger models.
Yes, they show results suggesting the advantage of this focused training scales with model size. It becomes even more effective for more capable models.
Which makes sense as the reasoning paths probably get more complex.
Potentially, yes. More complex problems might involve more nuanced decision points.
The paper also touches on some broader connections, right? How this entropy perspective might shed light on other things we see with LLMs.
It does. For instance, they suggest this might help explain why reinforcement learning sometimes generalizes better than standard supervised fine-tuning, or SFT.
How so?
Well, SFT often trains the model to mimic specific example outputs very closely. This can push the model towards high confidence or low entropy everywhere, potentially making it less flexible when it encounters a situation that requires a different path.
It learns one way to solve it, maybe too rigidly.
Kind of.
Yeah.
Whereas RL, particularly this RLVR, focused on high-entropy tokens, preserves or even tunes the uncertainty at decision points. It learns to find a successful path, which might involve being open to different options at the forks.
That's an interesting thought. It also helps explain why LLM reasoning looks different from, say, a typical RL agent learning to play a game.
Yes, because LLMs have dual constraints. They need to produce logically sound reasoning, but it also has to be coherent, readable language, integrating lots of background knowledge.
Right, it can't just output abstract actions.
So most of the output has to be low entropy to form proper sentences and follow linguistic rules. The high entropy gets concentrated only at the points of real logical ambiguity or strategic choice, unlike some RL tasks where uncertainty might be more spread out.
And finally, this has implications for designing better RLVR methods for LLMs.
It suggests that methods which naturally focus updates on more uncertain or surprising steps might be inherently better suited for this kind of task.
Like methods that use importance ratios.
Yeah, things like that. These ratios often measure how much the model's current choice differs from its original tendency. High entropy points, or points where the training causes big shifts, will naturally get higher importance. The paper suggests these kinds of methods might align better with improving co-true reasoning than, say, applying a uniform bonus for entropy across all tokens, which could disrupt the necessary low entropy flow.
So, wrapping this up, this deep dive into token entropy seems to show that making LLMs better reasoners via RLVR isn't about meticulously polishing every word.
No, it seems much more about strategically improving how the model handles those critical moments of uncertainty, the forks, in its thinking process.
It highlights that we need to understand the function of different parts of the model's output. Some parts just build the structure, while others are about making crucial choices.
And effective training seems to focus on getting those choices right.
It really makes you think. When you look at an LLM's reasoning or even reflect on your own thinking, can you spot those moments, those points where different paths are being weighed before one is chosen? Where are the real forks in the road?